Thank you for coming to my talk. I come from Croatia, Zagreb, Croatia. To Americans, I usually say it's a country near Italy, but we're in Europe, I guess you know, I hope you know where Croatia is. So we're a small company for 40-something people. We're also doing big data, among other things. And I'm running Apache Spark Zagreb group. We have monthly meetups. We try to at least have monthly meetups. I also wrote a Spark in Action book, and I'll be giving 3 ebooks at the next talk tomorrow. If you'd like to maybe to win one book, you can come to the next talk. Manning, my publisher, they prepared a discount code on the slide. You can see it down here. If you'd like, this is just an excerpt from data category of books. There's also data science, so you can check it out. It's 39% off all of those books, so you can use the discount code. And the agenda for today is a short introduction to Spark, what it is, how does it work, about Spark streaming, and I'm going to show short demos and one live example of a real working Spark streaming application showing some real-time graphs and parsing logs. But before we begin, please indulge me, and if you could answer several questions. If you've never used Apache Spark before, can you raise your hand? All right, 30%. You've played around with it on your laptop? All right. And you're planning to or already using it in production? Okay, quite a number. Thank you. So, what is Apache Spark? It's a distributed, general-purpose, large-scale data processing engine. So I'm going to unpack this just briefly. So distributed, obviously, you know, I guess you all know what it means. It runs on many machines inside some kind of cluster. It parallelizes computations. Everything runs in parallel. And the program is sent to data, just like in Hadoop. You don't send data to computer where the program is running. You send the program to data because it's much easier and efficient to serialize the program than the big data potentially. It's general purpose, which means that it's used across industries. You can use it for telco, for banking, healthcare, all kinds of analytical loads. You can read any kind of data, whatever you can do with Java, Spark, R, Python, you can do with Spark, except writing at some GUI. Let's say you would use some third-party tools for visualizations. And it also writes any kind of data to all kinds of storages. And it's obviously large scale. This is Big Data Conference. We all know about Facebook, LinkedIn, and Twitter, who grew at some amazing rates. I think the Facebook grew at a rate of about 10 users per second or something, which is huge. But also banks, healthcare, biology, telco, and astrophysics, weather, and so on. If your data fits inside one machine, you will probably get better performance because there's necessarily some overhead with all the organizing work inside the cluster and serializing tasks and so on. But if you're planning to grow your data, you probably can invest in Spark or similar engine even now. So it's a data processing engine. It's about processing data. It's not about an ERP system, or it's not a storage itself. It's not good for OLTP types of loads, which is kind of small updates to the shared state, but more for ETL, OLAP, batch processing. It's not a reporting system. As I said, you would use some kind of third-party tool to visualize the data and generate reports. Why would you use Spark? It's fast. Everybody knows, I guess by now everybody knows, it can be 100 times faster than Hadoop's MapReduce. It has simple and concise API. which is not that unique anymore. There are some other also frameworks that have similar conciseness, and it's a functional API, which is a good fit for these kinds of tasks. And it's a unifying platform, which means that you can run streaming tasks using Spark, which I'm going to show today, and you can use machine learning, Spark machine learning algorithms from inside these Spark streaming programs. You can use SQL processing for structured data. You can use graph algorithms and so on. So you got all of these features inside a single platform, and you need to, handle just one framework potentially. That's simplified a bit, yeah. And finally, it's gone mainstream. Last year or a year and a half ago, IBM pledged to commit 3,000 developers solely to Spark. They started Spark Technology Center in San Francisco, and all the Hadoop distributions include Spark. It's been integrated in many other tools and projects, and the user base and the community is just huge. So this is a kind of basic architecture. You have on the left side there's a client JVM, which is running a Spark driver, which is basically a Spark context object, an entry point to Spark API. You use it to connect to a cluster, which can be a Spark standalone cluster built especially for Spark, or Mesos or Yarn clusters. And the cluster manager from one of those clusters gives to the driver, to the Spark application, gives its resources, which are just JVM machines, which have, each of them has its memory, JVM heap, and some kind of slots. These blue and white boxes are just task slots for running tasks. Those are just threads, ordinary threads, but limited with some kind of parameters. And those blue ones are occupied currently, white ones are kind of free. This picture doesn't say anything about the number of physical machines. This is just number of executors. This can be all run on your laptop or on 5 machines or whatever. This is a logical image of Spark APIs, its components. There's Spark Core, which runs RDDs. RDDs are resilient distributed data sets. They are the main entry to Spark you work with. It's a distributed collection of data, which is resilient to errors and so on. There's also Spark streaming. I'm going to talk about it today. There's machine learning, MLlib and ML, Spark SQL for working with structured data, graphics for working with graph algorithms. So about Spark streaming. The basic idea is that you have some kind of input coming from, let's say, Kafka or Flume or Amazon Kinesis or flat files or TCP/IP connections, whatever, and it enters into input data stream, and it's shown as split in 3 mini batches. So Spark splits input streams into timed mini batches. In each of those mini batches, a different RDD is produced, or D stream, which is distributed stream. So you work with, I'm going to show you code later, so you work with those D streams. You write the program once, and it's executed in every mini batch. And it's you work with RDDs or data frames as you would normally do in batch programs. And then you can do whatever you do in those normal batch programs. You can, as I said, call some kind of machine learning model. You can call graphics algorithm. You can structure those data, work it as structured data with SQL, and so on. And then, of course, write to some other third-party system, to a distributed file or database or whatever. Spark streaming features, it works with discretized streams. It has receivers for various sources, as you've seen on the image. It has a special Kafka direct connector, which is more efficient. It connects directly in parallel to how many Kafka partitions Kafka topic has. Kafka Direct Connector would start as many, let's say, receivers and Spark partitions. You can save computational state over time, so you can maintain the state or number of certain things you counted from the beginning of your program and so on. You can use windowed D-streams, which are pretty standard these days. Lots of other frameworks have them, which enable you to count some objects or work on a state from just the last X minutes or seconds and so on. You can join streaming with static data. That's not that common with other frameworks maybe. And you can use back pressure. If Spark doesn't have enough resources to keep processing all the data that's coming in single mini batch, it can just stop reading, for example, from Kafka, and say, you know, wait a minute, I have to process this data, and then I'm gonna start reading again, which is a really useful thing sometimes. And Spark streaming is for half a second latency setup. It's not that good for less. In some cases, you can make it return your results in lower time, but mostly it's half a second and up. That's the usual measure, they say. And structure streaming is new in Spark 2.0. It enables you to look at streaming data as coming into a table. So just data is coming in and just appending to a single table, and you are just executing SQL queries on this table, joining it with other tables and so on. You really write a program exactly as you would on the batch data, and with just one magic line, let's say. So this is a first example of streaming word count. Word count is very often used as an example in these presentations, but it's for a good reason, because it's not a trivial thing to do in a distributed system. We have to combine all the different, the same words distributed across the cluster and count how many times each word appears. So what you do is you first have two import lines and then start a Spark context. SC variable is a Spark context, which is, if you're starting your Spark shell, it's already initialized in your Spark shell. And the first thing actually you need to do for Spark streaming is to create a streaming context. You tell it how many seconds you want the batch intervals to be. And in this case, this stream, distributed stream, is created from by reading a distributed folder. So Spark waits for new files to appear in this folder, and then it reads line by line and sends it to Spark streaming program. It doesn't, if there are existing files in this folder, it doesn't process them, and it cannot tail files. So just if you put new files in, it will pick them up. And then flat map is done on this file stream. This D-stream, each element of the D-stream is a line from the input file. And then each line is split according to white space. And flat map, what it does, it creates a, from each input element, it creates 0 or several new elements. And then for each word, we got words split by white space. For each word, it creates a tuple where the key is the word itself and the value is just 1. Then for each RDD in the stream, it reduces each stream of those tuples by key, so it has to group them by key inside a single partition. Each key goes in its own partition, and this adding function is executed on all the values of the same key, and the result is one element per unique word. And the value of those tuples are the counts, of course. So you need to start the computation, streaming computation. If you are running this program inside a standalone application on Spark cluster. If you're not running in Spark shell, you need to add this line await termination so that the application would stop the main thread and wait for the streaming computation to stop. Otherwise, in the Spark shell, as you will see, you don't need this line. Then you have a saving state. So time on this image goes from top to bottom, and for each mini batch, there are 3 here shown. Shared state is updated, and some different results. State can be updated, read from, and written to, and the results depend on the state as well as the input data. So the example is similar. You just also have this map with state at the bottom, which uses this update count state function, and it checks if the state exists for a certain word. It just updates the total. Otherwise, it leaves it alone. So it counts the words from the beginning of the computing processing, when the processing started. And there's the example for windowing. So we have a sliding window, the slide duration and the window duration. Window duration is the time for which you maintain your state, and the slide is by how much it moves every time. So in this case, the slide is 2 mini batches intervals long, and the window itself is 4 mini batch intervals long, and you get 2 outputs from this. This is the example. You have your just one function is different in this code than the other ones, and that's the window. You tell it how many minutes or seconds or milliseconds you want it to maintain the state for, and it produces a windowed dstream, a special dstream, which otherwise is the same as the other dstream objects. So here's a demo. Okay, you can see it. This is a Jupyter network running on a virtual machine on my laptop, and I'm using Spark kernel, which runs a Spark cluster in the background, Spark local cluster. So I already executed those 2 import lines. This here is just showing all the parameters from Spark cluster application, and now we need to create a streaming context. Okay, it's done. And the next line is showing top 5 most frequent words in a mini batch. This is the same snippet, almost the same as you've seen in the previous slides. So it just needs to compile it, and which is kind of slow on my laptop. Okay, it's done. And now I need to start the computation. Okay, so it's running. And the next step would be, I'm kind of short-sighted. I'm not sure I can see this myself. I have a TMP folder, and I'm gonna copy. I have files. Just a second. Okay. I have a files folder. I'm going to copy 2 files in this directory from the files folder. Files, okay, disclaimer, copy it here, and the Spark was supposed to pick it up. Okay. Sorry, where am I? Okay, there's the complete file. So it produced 1 line from the complete file with top five words from that file. I can do the same with do the same with the other file, and when it produced another line. So there are two lines for two input files. Now I can stop this computation by saying do not stop Spark context, only stop the Spark streaming context, and we are running this in Spark shell, so we can overwrite Scala variables. So we can create a new SSC variable with a new Spark streaming context and start the new streaming application inside the same shell. So the second one maintains the state for the whole duration of the streaming context. And I'm going to do the same again, so you'll see the difference. Okay. So let me remove the files. And I'm going to copy disclaimer file. And I think okay. So this is top 5 words from the disclaimer file. And it keeps changing the words with the same number because of the ordering, but it's the same top 5 words all the time. If I now add the second file, this will change, and you'll see a different top 5 words. So the last quick example is with the windowing. Is the same as you would guess, and okay. So I think this is too much, 20 seconds. It produces, it goes away, right? If after a window of 20 seconds, is it working, or what did I do here? Disclaimer, okay. Okay, it picked it up, and now I put the notice file. So after 20 seconds of window time, it will, those two okay, so the output changed after 20 seconds because the words from the first file went away. So we can stop this now. Oh, sorry. Okay. I'm going to just switch over to the next so that we don't have to wait in the quitter, oui. Okay, shut down. Okay, we're all set for the next demo. Okay, so I'm going to show you now the example application. So the point is application is, there's an input coming from a log simulator, which simulates users clicking on a website. It's coming into a Kafka topic, and there's a log analyzer application, which is a Spark streaming application, aggregating those logs, and it writes the results back to a different Kafka topic, and there's a web stats dashboard application, which is that's a Java web application, which is just stupidly transferring those results over WebSockets to clients, JavaScript clients, which are displaying it on a moving graph with D3.js framework. So the input looks something like this. It's a typical input that you would have in a web log. That's date, time, IP address. Session ID is usually not found in weblogs, but I put it in for, to show some things. There's a URL, the method used, the get, post, and so on, response code, and duration. And the output is the blue part is the timestamp in milliseconds since the epoch time. And there's a map, serialized map as a string, shown as a string, which shows a number of sessions, number of requests, current requests per second, number of errors per second, and some kind of ads shown on the website. If someone clicked on an ad, it counts those two. So the big point difference here is that reading from Kafka is pretty easy. You just connect to tell Spark or Kafka direct connector, where's Kafka, where's the topic, where's a broker or zookeeper, and that's it. It creates a D stream, and you can use it to count the process the input stream, whatever you like, however you like. But for producing, writing back to Kafka, it's a bit more involved because you cannot just Kafka producer opens up a connection to Kafka, and when you're writing a program in Spark, this program gets serialized and sent to the executors to a different JVM. So connection is not serializable. You cannot just send this open connection to a different JVM and expect it to use it. So you need to open up the connection from the executor itself. And it's not good to open a new connection for each element, input element. So the best thing to do would be something like this, which does, this is just a static object. Objects in Scala are just like static in Java. So it opens up just one Kafka producer per JVM, and all the programs reusing this class will use the single producer, which is, I think, the most efficient way to do it. Oh, okay. So this is the application. We have the same, almost the same imports with addition of some Kafka classes and Spark Kafka streaming, which since 2.0 I think is a different package. You need to, I already included all the required jar files in the Spark cluster, so we didn't have to do this. First, we create the Spark streaming context again. And Kafka direct connection, it's pretty simple. You just tell it where the broker is, and it automatically takes whatever the partitioning is for the Kafka topic and creates that many partitions in Spark. And the next line, parses the input line and creates log line objects from those lines. So this is a case class in Scala. This is all it takes to create a simple Java bin in Scala, and it will have all those members in it. So when the log stream here will have its elements will be objects of log line class. Okay, so the next one is we're counting web sessions. So first of all, we map this log stream and create a tuples from session ID and the time it appeared. And then we reduce it by key to find the last timestamp of each session, and then update state by key to, oh, I didn't execute the previous one, I guess. Okay. So this piece of code here will check if the old session exists or not, if that key already exists, and if it will check if the session is stale or not. If more than 2 minutes, let's say that the session timeout is 2 minutes. If more than 2 minutes was spent before the last session time, then we update the state and return none object, which is similar to null, and then that will remove that key from the state. And we do the same with, we just update the time if it's found. And in the second part, we count the log lines per second. This just maps it to, rounds up the time to a second. And combined by key, we just sum up all the counts of request log lines. And we do the same for errors. And now we map each of these to a map, and the timestamp rounded to a second is the key. So the map contains requests or errors, and the final, then we just union all those these streams together, and when we reduce by key, we just add all those elements to a single map. So the final stats, this stream contains elements that contain just one element per batch interval, which contains all those metrics together. And finally, we use the Kafka producer wrapper here to get the instance and send those serialized objects, string serialized to, okay, I forgot to execute this. Okay. Okay, it's done, and now I can just start it. And it will start reading the data from the input Kafka stream. So I have two more things missing. One is the Kafka. Oh, no, where is it? Okay, this is the Spark streaming dashboard. It automatically opens up when you start a Spark context and starts up the Spark Web UI. And there you can see the jobs running and so on. And if you're running also Spark streaming context, then it opens up this tab and you can use it to see what's the input, what's the scheduling delay, what's the input rate, processing time, total delay, and so on, which is very useful for debugging things. And finally, this is the started application, which is also running inside my virtual machine. And while this x-axis is moving, that means that the application is running. It's reading data from Kafka, and this output, this is last 100 lines from Kafka stats, the output from Spark application. If my Spark streaming application wasn't running, I wouldn't be seeing this. And the last thing to do is to run this simulator I wrote, which will start writing start simulator. It generates some of this traffic, and then now you can see it appearing. I'm sorry about this. This is due to delay from my virtual machine to my host machine in time, but so it's a bit delayed, but otherwise it wouldn't be here. It's my mistake, sorry about that. So you can see the number of sessions because the simulator starts 10 sessions, 10 users, and it simulates some kind of requests and errors and so on. So that's about it. If you'd like to know more, I have chapters 6 and 13 in my book, and all of this code is on GitHub, including D3.js and a log simulator. All of it is on GitHub. You can see the link there. Yeah, we're hiring. I know it's a long shot, but maybe it's a nice country. Who knows? If you want to work with Spark, maybe you'd consider this. I'm going to repeat this discount code here. And with that, if you have any questions.
I've seen that you have a lot of reduce by key and combine key unions as well. Have you, two questions, have you measured the ratio of shuffling that data for large volumes of data, because these are logs? And also, have you considered at any point to compare that with Flume interceptors and loading that into a key value data store and see the performance between them? So
I'm sorry, the first question was
yeah, if you have measured, you have done a benchmark for the shuffling of data, because you've got unions and reduce by key, and to see if for large volumes you actually need a lot of workers.
Yes, well, it depends on your cluster and your use case. I didn't do performance measurements for this case. We've done it on a different stream, doing similar things, but not that much computation or unioning, mostly forwarding to Cassandra and Elasticsearch, and it proved to be pretty good. And we did those joins and things in ETL for ETL type of for batch processing, not streaming. So yeah, you should try to minimize the number of shuffles you do in a cluster, whether you're doing ETL, batch processing, or streaming. So what you can do is partition your data so that all the RDDs are partitioned by the data which you use to join them, so that it's already partitioned together, so you can join them efficiently.
I was considering that in case of streaming, you haven't got control of partitions as much as you could have in batch, and probably maybe you can use the different options like Flume interceptors instead of having cross-memory events.
I'm going to check those. I didn't use Flume interceptors. I'm going to check those.
Flink.
Yeah. Yeah. Yes.
I wanted to know if you had done that. Thank you.
Any other questions, maybe? All right. Thank you very much. Come again.